So what do? First, you try to think of what are the possibilities that matter to what happens on the surface. Because life, as we know it again, is a surface planetary phenomenon. It doesn't occur in the center of the iron core of the planet. Well, there will be three generic possibilities. It's either the water planet, where the water dominates and half of the planet is water, or even 20% of the planet is water. It doesn't matter. It's just water all the way through, meaning that if you have the conditions for liquid water on the surface, which is the habitable zone, we still want to be there, you have an ocean which is about 100 kilometers deep. And about 100 kilometers deep, some funny things starts to happen. The water is now so dense under its own pressure that it solidifies. Even if the temperature is high, it solidifies into ice, but no longer the snowflake hexagonal ice that we are so used to like or dislike, depending on whether you live in Boston or this winter. But an ice like Ice 7, which is a cubical crystalline structure, denser than the liquid form of water, sits on the bottom and doesn't care much about whether the temperature is high. It's all a pressure phenomenon. That's very different geochemically, it turns out, from the state in which that ocean covers the entire surface, but still is less than 100 kilometers deep, and what is on the bottom is rocks. So then you have direct contact between the rocks and the liquid water. And suddenly it turns out is even different from the case which we have here on Earth, and curiously we've always had on Earth from the geological record, which is the case where some of the rock is always sticking above the surface of the oceans. So when you look at this picture, two questions beg to be asked. The first one is there any fighting chance for the Earth case to happen at all? I mean, it's such a very fine-tuning case. You know, you just have to have the right amount of water to cover thinly half of it, but not the other half. I mean, it takes very little more than the 0.02%, 2% of a percent, to cover the entire surface, and then you're in type number 2, the middle case, where the geochemistry changes. Or you're completely dry, no water at all, or nothing to speak of, Mars. So that is the first question. The second one, which we really need to know if we are searching for life remotely on the surfaces of distant planets, is what controls the atmosphere? Because that's what we are going to see. We're going to see the atmospheric features and the surface features. And you know, each one of those three scenarios, there is a different physics that controls what happens in the atmosphere. And we understand quite well now the Earth case. It's called the deep water cycle. Ignore the gory details here. This is an actual picture from a publication. But it is good enough to show you the basic idea here. Water that you see on the surface is only temporarily on the surface, but it cycles through not the center of the Earth, but through the mantle, the interior of the Earth, below the crust, comes back again, and what you see is a cycle which has negative feedbacks. If too much water gets drained out of the surface, these negative feedbacks push more back to the atmosphere and to the surface and vice versa. Very interesting system, and it makes sense in a general way, not just for the Earth as a unique planet, but for this kind of planets which have a small amount of water. And it doesn't have to be anymore 2% of 1%. It could be even 1% of water, just most of it will sit in the mantle, and only a little bit will be on the surface, so that this cycling can continue and some of the rocks are exposed. Very interesting, but it works for one Earth mass, Earth composition. So we wanted to know, is this same idea going to apply to super-Earth, because we see planets there bigger than the Earth, 20% bigger, 50% bigger. Interestingly, the same feedback mechanisms for the deep water cycle seems to apply to those bigger planets. Very interesting and hopeful that the Earth is not some freak accident, but there is a whole family where if you have a small amount of water, a few percent, you will have a picture like that that is more common, just either a complete water world, no continents, or a world in which all the water is locked in the mantle and there is nothing on the surface. So that's very important because it then answers the second question, which is what would control the geochemistry of the planet on the surface? In other words, the atmosphere. And here, we again take a cue from something which we understand pretty well here on planet Earth, which is the carbon cycle, also known as the carbon dioxide cycle. Just briefly, the carbon dioxide as a gas is a very common gas in any rocky planet. It's not just unusual initial conditions here on Earth. So that very common gas would be in the big reservoir of the interior of the Earth, finding ways to come to the surface, usually through volcanoes and mid-ocean ridges, then accumulates in the atmosphere, sometimes a little bit too much for comfort. That's the same reason why carbon dioxide is not so good when you overdo it, because it's a greenhouse gas. But it's a self-regulating cycle because it then rains down, and where the red arrow shows you, the important chemical step there is that there is this interaction between the carbon dioxide dissolved in water that reacts with the minerals, silicate minerals of the surface, the rocks generally, and then completes the cycle as the plate tectonics renewal of the crust continues. So that works if you have exposed rocks, but what if you don't? If you don't have exposed rocks, as in a water planet, you're missing that important step. So the whole cycle has to be different. And that was a question which, again, was not addressed because we didn't have water planets in our solar system, so why bother study them? Study something which doesn't seem to exist. So the first part was there will be a layering of ices. I told you already about those high-pressure ices before you reach the silicates where the carbon dioxide will come from. The first order question is any carbon dioxide going to make it to the surface through the ice? The answer is yes. That ice, as solid as it is, like many other things, convects slowly. Takes about, as you see here, maybe 1 million years. But hey, 1 million years in the age of a planet geological record is nothing. So yes, the first thing reaches the surface. It would reach the surface, but in a very different way than what happens here on Earth. Because under those high pressures, water, being the polar molecule and polar liquid it is in solid forms, actually would encase the carbon dioxide or methane or molecules that are volatile and want to come to the surface in particular crystalline structures. I pushed the wrong button here. There you go. We call them clathrates. And by the way, the low pressure forms of those clathrates have big interest to the oil extraction industry. If you remember the problem we had in the Gulf of Mexico, a lot of the problem that was dealing with what was happening near the bottom there with those forms of ice which are rich in methane, natural gas. But if you go to those planets which have higher pressure than anything that we've ever experienced or experienced here on planet Earth, you end up with forms of clathrates which were never studied before, like field ice, where the water arranges around the molecules in different ways. And you start having interactions between methane and carbon dioxide, which turn out that a very similar feedback mechanisms as to the deep water cycle, which works for the Earth crust, where clathrates are not important in that sense. And so the final point of this, it turns out, is that yes, we are starting to understand what would control the atmosphere in a water planet, and that will be the clathrates, the forms of water that control which gases reach the surface and which are essentially encapsulated into the interior. And so now it seems that we will be able to tell the difference between a water planet and a rocky planet like the Earth, even though we only have the radius, the mass, and one measurement of the abundances of gases in the atmosphere. So you're trying to control 3 parameters: water, iron in the core, and silicate. With 3 variables, you can solve for that degeneracy which currently exists. So then the question is, do we have enough of those planets to really hope to have a search like this? And the answer is yes. Thanks to Kepler, we found, and that happened really in the last 2 years, that our initial estimates of how common Earth-sized planets are in the habitable zones of nearby stars were very underestimated. They were very low, very conservative, as we would say. So the current estimate is about 100 times higher than what our original values were before the measurements were complete. And it's likely that that number may go even further up. So for the kind of planets that are interesting to the search for life in the universe, in our own galaxy, we now estimate that probably between 1 and 5 billion planets are available currently for this exploration. Now, this is a very large number, but just remember, astronomy is about large numbers, and 10 to the 9, even 5 times 10 to the 9, meaning billions of planets, is not necessarily a large number in a very, very large galaxy. So what really is the game changer that happened in the last year or so is, what does this number mean to our chances to find some of those planets right next door? And this is what made the big difference and what is making the big difference. And that's why I'm talking to you about this today. Because 3 years ago, I would have told you this, but I would have told you have to wait about 20 to 30 years before we can reach the nearest of those interesting planets and do the studies we want to study, because our technology is not there yet. What this new measurement did 2 years ago is to change that timetable from 20 to 30 years to 5 to 10 years. So now we have the technology, even with telescopes like the Hubble and some of the ground-based telescopes, to study the nearest of those planets, because they're much closer to us than we thought 3 years ago. And that changed the game, both by shortening the timescales, but also giving us the confidence that we can do it, and we have the tools to accomplish this. And immediately, as this was coming through the data with the Kepler mission, which I was honored to be on the team, a smaller group from the East Coast already proposed to NASA to take advantage of this. That is, to go and find those nearest planets, which, thanks to Kepler, we know should be there. We just haven't found them. The Kepler planets, because it was essentially a statistical mission, were selected to be farther away so we could have good controls and do the statistics right. Now we know the statistics. We no longer want to improve the error bars on how common Earth-sized planets are in the galaxy. Now we want to find the ones which we can study. And this is what this space mission, already approved by NASA and going to space in 2 years, summer of 2017, is supposed to do. And we're pretty confident that it will be successful as long as everything goes well with the launch and goes to the right orbit. Because the statistical result from Kepler is very strong and very reliable.